Hi there, this is Dr. Embody with Project 4. In this project we'll be working with functions, and in fact we're going to work with some trig. We're doing approximations of some math and trig values using some summations. You might have seen them before in one of your math classes. But the idea is to write some functions just using this old technique of approximations with sums. So let's take a look. For example, here's a tangent formula, and it's expressed as a summation. So if we wanted to do an approximation of the tangent of x, we can do the summation of these terms, which is a bunch of the terms: first term, second term, third term, and so on. And that's a pretty common thing to do in mathematics, a way to get approximations. Now, one of the ones that we have is the Euler one, so what I thought I'd do here is, rather than doing one of the ones that's in the project description, let me just do pi. Okay. Now, one of the things that we have in here is that sometimes these are expressed as some, in this case, 0 to n, and here we can see that this goes up to infinity. And so what we do there is we're going to expand the series until the next term is less than 1e to the minus 7, 10 to the minus 7th, and in fact we say that term won't be included in the sum. So with that, let's take a look at doing pi. Now, if we look up under on the internet, for example, under Wolfram's Math World, here is what the pi expression looks like. And quick look at this. It's got it's -1 to some power, and if you take a -1 and you raise it to an odd power, it will be negative. An even power will be positive. So this value alternates between positive and negative values. In fact, there's a graph here. You can see it bouncing back and forth that way. And then 2 to k minus 1, that in fact will always be an odd number. We're going to add these up. This shows it going to n. We're going to do it to some epsilon. And let's take a quick look again by hand what these might look like. So we start with k equal to 1. And when k has a value of 1, this is -1 squared, which is a positive 1. And then it's 2k minus 1, which is a 1. So the value when k is 1, the value of this is the term is 1 over 1, and which of course is 1. All right, so if k is 2, then we have an odd number, so there'll be a -1 in the numerator, and 2 times 2 is 4, minus 1 is 3, and we have the next odd number, and that will continue in that pattern. Alternate, the numerators alternating positive and negative, and the denominators being the odd numbers, because 2k minus 1 is an odd number. So we can recognize these. That has a value of 1. This will be 0.33. Repeating, that's 0.2. I don't know what 1/7 is, something or other, and then 1/9 is 0.111 repeating. So there's a few values there that we can check, and of course we can easily check the 1/7, but I'm just not going to at this moment. So so we have a few things here. We have I'm going to calculate a value of pi. That will be my sum. I'll start that at 0. We're going to need a value of epsilon. 1e to the minus 7. Okay, so now I have a value of epsilon. So I am going to, and I'm going to loop while my term is greater than epsilon I'm going to do something. What am I going to do? Well, if we look at our formula, we have to have a k, so I better have a k in there. And the k started at 1, and we're going to have to increment that. And then we're going to need a term. Well, if I'm checking a term here, I better have a value for it here in order to check. And as we calculated before, when k was 1, the value of the term was 1. The other thing that we're going to do is it said that we're not going to include the term. So my pi will get whatever term is, and then I'm going to get the next term. And what was our term? Well, there was a -1 raised to the k plus 1 value, and this all made up the numerator, and my denominator was 2 times k minus 1. All right, so there's the term. My numerator is -1 to the k plus 1. My denominator was 2 times k minus 1. Let's check that. -1 to the k plus 1, 2k minus 1. And then we're going to return 4 times the value of my pi that I have here, right there. Notice that there's a 4 out in front there. So I'll add the terms up, multiply it by 4, and let's see how we do here. If I run this, I can say, all right, now, so when I have functions like this, notice I don't have a main program. When I run it, nothing happens. Well, what I can do is I can actually execute that program. So let's execute it there. And I've got a key area there. Let's just restart the kernel. I was playing around with some stuff there. Let's try this again. And it gave me the value of 4. Whoa, that wasn't what I was expecting. What happened here? Well, I was messing with my my variable explorer here, so that's not working at the moment. So let me just put in. I was going to show you doing this in the debugger. Let's see what these terms are. Maybe we'll do it down here. And now when I run this thing, we go, and we see that my term is -0.333. So what happened here? So notice that first of all, we did get we started with the first term whose value was 1, and then we calculated the second term here. That was the second term, and we expected that to be -1/3, and it is. But my loop stopped. Why did my loop stop? Well, -1/3 is not greater than epsilon because it's a negative. Oops. All right, so I better fix that. And one way we can fix that is to make sure that we're considering the size of the term rather than its actual value. So let's try this again. Oops, let's not. I'm going to, I don't want to print a gazillion values here. And so now if I try some pi, and notice the pause, right? Nothing's happening. Well, actually a lot is happening, and there we go. We can see we have a value of pi. If I wanted to check, I can see what the math.py value is. And you can see where it's correct down to this value here. So we're down to about 6 digits of precision there. So that's pretty good. If I wanted more precision, I can just change the epsilon. So there's how to take an expression like this as a summation and write a function that gives us a value. One thing that I want to point out, we give you something to start with, and we even define the epsilon there for you. Notice this thing down here at the bottom. There's 2 things of interest there. First is that we have a main program, okay, and that's where the driver part that will call our functions. And then you got this weird thing down below, this thing. All right. And what this is saying is that if I execute this program, proj04.py, then then the name will in fact be this localized Python variable main. And so it says, okay, you're running this program, so what we're gonna do in there is we're gonna call your main function. Why do we do that? Well, we do that because the test cases just want to run the individual functions, and they don't want to run the main. And so I can then import this. So if I do this as an import, this will be false, so the main won't run. And that allows us to test these functions individually. So the short answer is that if you don't have this, then the individual function tests on Mir won't work, and weird stuff will happen, and they'll always fail. Hopefully that gives you enough to work with. Good luck.